The triac is the one that we're going to look at next. And I want to start off by showing you the, I'm going to show you the symbol for the triac. And it looks a little bit like this. It's kind of interesting because when you look at it, it almost looks like a diode, sort of a symbol like this. You know, you see this coming up like this. And then from this side, you see another diode symbol like that. So it's kind of the two of them. And then it goes like this, goes across to here, and there's another terminal there. Now this device is a 3-terminal device, and so at some point you're going to see a gate on it. Okay. Now a triac, and it's right in the name. Triac. Okay. This device is for use in AC. And so that means that the current will go this way on one alternation, and then the current will go this way on the next alternation. And what will control how much of each alternation is allowed to be conducted will be when the firing takes place on the gate. Now, the interesting thing about it is that the gate, which is right here, one gate is responsible for firing in either direction. So in other words, there'll be a gate signal that goes in that allows conduction one way, and then in the next alternation, the gate signal will actually be allowed to pass out through the gate. So the gate is also going back and forth, current in and out, and the actual triac goes back and forth. Now this can be, these are called MT1 or sometimes just T1, and MT2 or sometimes just T2, and it just stands for terminal. Now, the thing that I do want to say, and you may have discovered this already as you were doing your symbols research a little bit earlier on, is that they're not real consistent in terms of where the gate is located. I've seen it located on the symbol. I've seen it located on the T2 or the MT2 side, and I've also seen it located on the MT1 side. And so there doesn't seem to be too much concern. And if you think about it, it is an AC. It's a back and forth device. So and the gate current can go in or out. So probably not a big deal. But I do want to show you the semiconductor layers of this device, just to give you an idea how they're arranged. And it looks a little like this. Here's one part of it. Okay, so this is a chunk of semiconductor material that I'm going to divide up into 4 layers, and then I'm going to draw another chunk of semiconductor material that I'm going to divide into 4 layers. And then I'm going to label the layers as to their semiconductor type. So I'm going to start over here with P, N, P, N. And then in this one, I'm going to start on this end with P. I'm going to put N, P, and N like that. Now imagine that internally inside of this component, you were to take and connect these 2 points. And then you were to take and connect these 2 points. And I'm going to tie a lead over here. And I'm going to tie a lead here. Okay. Now, in order to match this symbol, what I'm going to do is I'm going to call this MT1. And I'm going to call this MT2. And then I'm going to show you what happens inside here. There's one more connection that gets made, and it looks like this. This is tied across here, and this comes out like this. And that's the gate. Okay, and so this is how the semiconductor layers are put together. Now I got a question for you from everything we've already talked about with thyristors. Doesn't this look a whole bunch like an SCR and another SCR inverse parallel connected? Okay, and so the truth of the matter is that a triac is essentially identical to two parallel, inverse parallel connected SCRs, with the interesting exception that the two SCRs each have their own gate. And so you have to hook up a trigger circuit that will adequately fire one SCR in one alternation and then fire the other SCR in the second alternation. This one, the gate is hooked up so that it fires one SCR, and then in the next alternation, the same gate just fires the other SCR. So, it's AC. We got current going this way and then this way. And so the nice thing about this is that this is literally one component with three leads, and we can achieve, as long as we have the proper trigger circuit, an RC, resistance capacitance trigger circuit, we can literally have full phase control. Now there are many applications for this in what we would call lower power circuits. Now I think I mentioned that if you take two SCRs and you put them together, that's typically higher power, kind of 50 amps and above. And I think that it depends a little bit who where you get your source of information, but it's generally considered to be in about that 45 amp range, 45, 50 amps. Anything smaller than that, you can actually get triacs that will manage that amount of current. And so the triac, obviously much simpler than using two SCRs and doing all the connections and getting your dual triggering circuits and things like that. So very, very interesting component. Used, I'm going to say 45 amps and less. Okay, 45 amps and less. And so lower power circuits. Now, what are the applications where we would use this? Well, let me start off. We can name a few. Heating elements. So, when you look at resistive type heating, even inductive type heating in range tops, where they're, you've got your dial on your stove and you can dial it from 1 to 10, depending how fast you want to burn something. And what happens is inside there are triacs that are varying the amount of effective voltage that goes into the element. Okay, so that's one heating elements. And by heating, I mean sort of cooking elements, right? Also used for small motor control, okay, small motors. But one of the largest applications of the triac, and this is a big one, everybody's interested in this stuff, and it's light dimming. Light dimming. So lighting controls a huge consumer of triacs, okay? Now, triacs are an interesting circuit. When you get into the triggering circuit, we need to use one particular type of triggering component that goes in series with the gate. And that component is there, and it's there to control to a very, very small level the amount of gate current. Now we can also use the same component in SCRs for triggering, although in many cases we're okay just with the resistors or resistor capacitor, but this lowers even more the amount of current. This device looks like this. And you're probably thinking to yourself right now, okay, that looks like a normally open contact. Hang on, I'm not done. This looks like this, and this looks like this. And you go, oh, wait a second, that's going to be another triac, but it's not. That's where I'm going to stop right there. That's the component right there. And this thing is what we call a triggering device. And this is called a diac. A diac. And a diac has no gate. Okay, so I'm going to describe to you in a couple minutes exactly what the diac does. But let me finish first of all overall with this. So once we know we're going to put a diac, and it's going to be it's going to be connected in series with the gate of the triac. And between these two components, this diac and triac, which is going to give us a very fine, accurate gate pulse to the triac. The triac is going to give us this seamless full phase control. And so this is going to make a perfect, voltage graduation controller. And so this is actually something that in lighting circuits, in light dimming circuits, this is actually usually you can get it in a single component that really looks like this. It looks like this. Okay, so there would be one lead, and there would be the other lead, and this would go like this, and then internally we would have this, and this would be the last lead right there. And so this would be MT, in our case I've been using 2, MT2, this would be MT1, and this would be the gate. So it's actually a triac diac pack, and it's actually assembled in as one, almost as one component. Okay, and so these are used extensively in lighting control. So the actual downfall, I guess I might say, of this particular component is there's one thing about it. The frequency that you can use this in, the frequency of control, is not very high. And the reason for that is that as the currents move through, they're going at one point they're going this way, then they're coming this way, and the gate current is coming in at one point and then going out at the other point. And so what happens is in the actual layers, it's pretty sophisticated the way that the current moves. And if you start trying to press them too hard to have to switch too quickly, the phase control kind of breaks down and they don't work anymore. And so they are limited, and I'm just going to write this here, to about 400 hertz. Okay. Now, on the flip side, if we wanted to compare this to the SCR, okay, an SCR is able to switch its switching frequency. Okay, so this is the SCR. So there's the gate, anode, cathode, and this is the SCR. This one can be switched at a frequency of up to 25,000 hertz, or 25 kilohertz. 25 kilohertz. And so, the triac much slower in its capability, and it's simply because it just gets confused inside of the process of what's going on if you start trying to do it too fast, and it breaks down. So that gives you a little bit of a description of the triac. Remember, it's an AC device, and so when we use this, we're actually measuring not average voltage anymore. We're actually measuring effective voltage. So the output voltage from the triac is going to be an effective AC voltage. All right, let's take a look at the waveforms that we see from a triac. Okay, and so we'll kind of get an idea. First of all, I want to show you when you compare a vector, basically a center origin vector diagram, to an actual waveform. This is always an interesting comparison. Let me first of all show you this one. Here's our X and our Y axis center point, and we always start with our vectors pointed like this at 0 degrees. And then the vectors are considered to turn in this direction, and this is 90 degrees. Then that moves down here to 180 degrees. Then, of course, to the full negative y, 270 degrees, and then back up to 0, okay? Or 360 degrees. Now, many of you are going to recall we called this quadrant 1. We called this quadrant 2, this quadrant 3, and this quadrant 4. And so what I want to show you is this. When it comes to the AC waveform, and we talk about control and the ability to control, we look at it in the same way. So a triac used with resistive only triggering, okay? So with resistive only, would only be able to actually control this quadrant, because with resistive only, we can only control up to 90 degrees, right? So this is actually considered to be quadrant 1. It's from here to here. And so with resistance only, we would be able to control this quadrant. Now, if we, that's our actual control of when the firing angle is right there. Now, if we get it to fire, yes, it does conduct through here, but our actual control with the firing angle is only up to here. Because if we don't fire by here, we will have no output here. So we must fire by 90 degrees. Now, if we have resistance only, here's what happens. We'll get control in here, nothing here, but then we'll have control again here. Okay, so we will again have control in this quadrant, which is quadrant 3. So with resistive only triggering, we'll gain control in quadrant 1 and quadrant 3. Now, if we use resistive and capacitive, then we're going to gain control into quadrants 2 and 4, and also including 1 and 3. So when we move to this, we just really add the capacitive part of it, just adds control into quadrant 3, quadrant 2 and quadrant 4. Okay, so we add control, and now we have absolute full phase control. So it's just to give you an idea of how the range of control is with the triac. Now I want to continue on with a little bit of a better explanation for you of the diac. Now I just mentioned the diac briefly a few minutes ago. I said that it was used as a trigger, basically a triggering device for the triac. And so what I want to do is I want to give you now a little bit better explanation of this component. So here's the actual, here's the symbol for it. Okay, there it is, the diac. Now let's talk about the ratings of the diac, and also I want to talk about really essentially what it does. How does it work? Now, one of the components that we looked at earlier was called a Zener diode. And a Zener diode looked like this, if you recall. And what I'm going to do is I'm going to show you the diode like this. And it had a couple of little arms on it like that. And here's going to be the load. And here's the interesting thing that would happen. This will be the current limiting resistor. This would actually be the load, okay? The load was actually always in parallel with the Zener diode. So this was one application. And in this way, this Zener diode would actually, we would have a variable voltage source here usually, something that could be moved up and down. And once we got to a certain point, this voltage, as soon as this started to conduct, it would stabilize the voltage, and the voltage wouldn't change anymore across the load. The interesting thing to remember is that this had to be hooked up reverse bias. Reverse bias. And so the important thing to note is that it had what we called a Zener voltage. A Zener voltage. And the Zener voltage was literally, you know, it was its reverse. In a regular diode, this would be its PIV, and it would be a very high value. But in the Zener diode, it was specially doped, specially designed, and so they could make this reverse voltage of the Zener diode some very specific value. So you could get, you know, 1 volt, one's 2 volt, one's 10 volt, one's 12 volt, one's, and so on. So let's say that you had a Zener diode that had I'm just going to say a 12 volt, okay? Let's say you had a 12 volt Zener voltage. What that means is that if you started to apply voltage, and let me just show it to you over here. If you started to apply voltage to the Zener diode in this way, like this, and I'm going to put a resistance in there so that we don't get a short circuit. What would happen is the voltage would actually start to rise. Okay, so the voltage would rise. And if you actually look at the voltage across the Zener, it would look like this. Let's say that this is 15 volts up here, okay? So I've got 5, 10, 15 volts. So as the voltage rises, here's what happens to the voltage across the Zener. It goes like this. It goes 5, but this, you know, it's like there's an internal pressure, and so it's just blocking. Okay, 9, still blocking. Remember I said it's a 12 volt, right? 10 volts, still blocking. All of a sudden I get to 12 volts, which is about there, and the voltage supply will keep going up, but the voltage across the Zener goes like this, and it sits at 12 volts. So that means it's kind of like, you can think of it as a door. Think of it as a door with a fairly heavy spring here, and this door is going to stay shut until you get to 12 volts, and then the door is going to go bang like that, and as long as you have 12 volts or more, that door is going to stay in that position, and you're going to have flow. As soon as your voltage drops below 12 volts, bang, the door is going to shut again. Okay, that's what a Zener diode does. It basically, it opens up, it starts to conduct at its Zener voltage, and as long as it has that much voltage on it or more, it's going to conduct, okay? Now, a diac does exactly the same thing, but with a Zener diode, if you hook it up reverse bias like we did, like if this is hooked up reverse bias, then you'll have its Zener voltage in one direction. But if you actually hook it up forward bias in the other direction, it has a 0.7 voltage drop, just like a regular diode. So you must use it in reverse. A diac is like taking two Zener diodes and hooking them up nose to nose. So inverse series, okay? So this is like two Zener diodes, inverse, so meaning opposite directions, series, so nose to nose. And now what happens is, guess what? This is an AC device. So you use it in AC, and that's why we can use it with the triac. The triac is an AC device, and we know current has to be able to go in and out of the gate, and so the diac has to be an AC device to let current in and out at a specific point in time. And when is it going to do that? Well, when it reaches its voltage breakover, which is exactly the same. It's a different name, but it means the same thing as Zener voltage means in the Zener diode. So in other words, imagine that you have this. This is a simplified version, okay? There's my spring door. This diac is shut. It is a 34 volt diac, 34 volt. So that means that as I apply voltage in this direction, 10, 15, 20, 25 volts, absolutely nothing, no current will flow through that diac. All of a sudden, when I get to 34 volts, and I'm pushing from this side, all of a sudden the door goes bang, it goes down. So we've overcome this spring, okay? So this spring goes and bang, down it goes. Think of this as a 34 volt spring. So it goes down and it starts to conduct. Now, seeing as it's an AC circuit, we know that the waveform goes up and then it'll come down. So what happens is it'll go up. As soon as it gets to 34 volts, it will start to conduct. It will conduct until you reach the same point over here as it's going down. Now, as soon as it's going down towards 0, this voltage is going to drop below 34 volts, and the door is going to go back up and close. Now, we're talking about a waveform that goes this way, like this, okay? So now we're going to put pressure from this side, and guess what? We've got a 34 volt spring on this side too. And so now the voltage is rising, 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 10, 15, 20, 30, 31, 32, 33 volts. Still no conduction. All of a sudden we hit the magic 34 volts and bang, goes down the door this way. And we conduct in this direction. So it's literally the same as the two Zener diodes connected like that. Now this voltage breakover is the same voltage in either direction, okay? So it works the same. So it's really a voltage sensitive, kind of a flow switch. It's gonna hold closed till it reaches that voltage. It's gonna open. It's gonna do the same thing either way. Now, the interesting thing about this is that this value, this voltage breakover, okay, this is breakover, so the voltage breakover is designed into the diac. So diacs, depending, they can be very, very small components, sometimes about that big. So the one that I use in the lab, you can barely see it. So imagine this, and it's a 34 volt. Well, that's what you get. You're designing a circuit, and that's what you need. You just buy that diac and you use it. If you actually need a 12 volt diac, then you check your catalog number carefully, and you order a 12 volt. So you can get another diac that is a 12 volt. You need a 72 volt diac, well, then you order a 72 volt diac. Whatever you need, you have to get that specific value, and it doesn't change. It's manufactured in that way. So you basically have to look at your circuit, see what the circuit design is, and make sure that you have the one that you need. Now, you know what? In many cases, that is perfectly sufficient. So many electronic circuits, you can hook them up, and as long as they operate according to your design, you don't really need to change that too much. But we all know that adjustments and having options is something that everybody likes. And so the next thing that we're going to take a look at, the next component, is called the UJT. And I'm not going to spend too much time on the UJT, but let me explain it like this. First of all, this stands for uni junction. So in other words, one junction transistor. Now, let me briefly stop and ask you, how many junctions do most transistors have? Okay, so if you think about it, most transistors have two junctions because most transistors are 3 layers. So 3 layers, 2 junctions. So this would be, if this was an NPN, this would be N, P, N. I could call this the emitter, I'd call this the collector, and I would attach the base over here, okay? Now a UJT is a uni junction, and so to kind of state what it should be sort of obvious, I guess, that means that there's only two layers. And so interestingly enough, it looks a little bit like this. Okay, so you've got two types of semiconductor material. Now let's just say that this was p-type, then this would be the n-type. And this right here would be that single junction. That's the junction right there. Okay, so just one junction. But interestingly enough, has three leads. So one lead would attach here, one lead would attach here, and another lead would attach down here. And this would be called the emitter. This would be called base 1, and this would be called base 2, like that, okay? Now, the actual symbol is drawn like this. So this just kind of gives you an idea of the layers. The actual symbol looks like this. It's kind of squared off like this. B1, B2, and then you've got this. And this is the emitter. And there's an arrow normally on the actual, on that emitter lead. Okay, so that's the symbol for the, for the uni-junction transistor. And what I'm gonna show you is essentially not really how this connects, but I want to just explain to you what the difference is with the UJT. First of all, the UJT is a trigger device exactly the same as the DIAC. Trigger device. Okay, it does the same job as a DIAC. In other words, it will build up to a breakover voltage in one direction. So it's used in AC. Okay, this is an AC component also, works in an AC circuit. It will build up to a certain voltage and then break over and allow current. Then when the voltage drops, it closes. Then as the AC reverses, it's going to build up voltage and start to conduct in the opposite direction. The only thing actually that's different, operation-wise, the only difference between the UJT and the DIAC, okay, here's the DIAC down here, UJT here, DIAC here. This one, the DIAC, has a fixed VBO. It's by design when they make it. This one, because of this interesting circuit, you can actually hook this up, get a couple of resistors, compare their values, and I'm not even going to go into the circuit for this, okay? I'm not concerned that you know how the circuit's hooked up, but what I do want you to know is that this one has an adjustable voltage breakover. Okay, so the UJT, its breakover voltage can literally be adjusted. So this would probably be used in circuits that are a little more elaborate and things where you need to be able to compare and make adjustments in some particular part of your circuit. Well, then a UJT is going to be the thing that you're going to use in that case, all right? So not really a lot to say about that, but I did want to just show you the comparison between the two trigger devices that we looked at. And I believe that the UJTs were, I think you did look at the symbols for one that is basically a P channel and one that's an N channel when we did that first assignment on symbols of electronic components, okay? So in terms of the UJT, that's about it. Now I have one component left, and it is the LASCR. So let's continue on with that right now. Now, we know that the SCR is essentially like a latching relay. Latching relay. In other words, when we apply voltage to it, it blocks. As soon as we give it a gate pulse, it turns on. And it doesn't turn off until, first of all, if it's in DC, it doesn't shut off until we force it off by dropping the current below the holding level of current. Or if it's in an AC circuit, then line commutation. So when it reaches the end of the alternation, it shuts off. So what is the difference then with the LASCR? And so first of all, here's the symbol, of course, for the SCR: anode, cathode, and gate. And now we're going to move over here, and this is going to be the LASCR. And the symbol for this one, quite similar, looks like this: anode, cathode, and gate. And two little arrows pointing in to that junction. So whenever you see this, there's something interesting going on. Many of you are familiar with this one. This is a diode, right? Diode. This is a light emitting diode. So if light goes out of the diode, well, we show it going out. This is actually a light activated SCR. So that means it actually has to have light coming into it to produce its gate current and be able to actually fire. It fires by voltage that is created. Well, I say it's actually current, gate current, that's developed internally by voltage that is produced by light falling on the junction. So let me show you a little bit what the actual component sort of looks like, okay? We'll look at it like this. If you were to actually look at the layers, it would be something like this, okay? And there's many sort of different designs and ways to see this, but I think this one kind of makes sense. You can kind of picture it. Imagine this. Right here, here's the junction between the inner p-type layer and the outer n-type layer. Okay, we always call this the inner p and the outer n, whereas this end is the outer p and this is the inner n. Okay, so you know exactly what you're talking about. Now the gate is typically attached right here. The anode is attached to the outer p and the cathode is connected to the outer n. Okay. Now what you have here is literally the junction right here. And so what they do is they'll set it up so that there's as much junction exposed as possible, and they put actually a lens on here. So what happens is light entering to this, once it comes into this lens, it focuses the light in this way on the junction, and there's a material in there exactly like the material is essentially the same thing that they're going to be building solar collectors out of. Okay, so a little bit of that material that literally takes light and creates voltage. And so the voltage that is created in this junction, so we're going to have E generated, okay, by the light. And it's by the light actually falling on the junction. E generated. That's going to produce I, and I'm going to call that I of the gate, because that's actually the current that will actually fire this SCR. And as soon as we get enough voltage to give us enough gate current that it meets the requirements of this gate, then this thing is going to fire into conduction. And after that, it's going to latch on and it'll stay on until until this current basically falls, until this falls below its holding level. So it operates in every way like an SCR. The only difference is that the voltage on the, that comes in here that basically produces the gate current is generated by light instead of being applied from a separate source into the gate. So quite interesting. Now we go, what is the purpose then of the gate terminal if we don't actually really input a gate signal? And it's a good question. And here's actually what happens. Let me show it to you like this. Typically what they do is they put in here a resistor. And then they take this and they ground it. Now remember that at some point over here, this should also be grounded, okay, in terms of your circuit. So we go, okay, now what's that gonna do? So let me walk you through this and you're gonna see, it should make sense as to what's going on. So let's start by looking at this. Let's say that the amount of current that we need to actually fire the SCR is 150 microamps, okay? 150 microamps required to fire this into conduction, okay? So what happens is, let's say that it's, let's start with darkness, okay? Let's say there's no light. And so this is not, it's not conducting. It's not conducting. And so what would happen is if you were using this for night lighting, for instance, you would have this set up in a circuit. This would be a very small current. This current through anode to cathode is normally between 1 and 2 amps maximum as far as commercially available units. So it's really small current. So if you had a 15 amp lighting circuit, you can't run it through the SCR. So what you have to do is this current would actually be operating just the coil of a small relay, and then that relay might have 20 or 30 amp rated contacts, okay? So just imagine this. Imagine it's dark. This is off. This is not conducting. So you would want the output of this probably connected to a relay where if it's de-energized, it would have a normally closed contact that your lighting circuit would run through. So your lights would be on when this was not conducting. So come morning, come sunrise, you start to get a little bit of light, okay? And I'm gonna show that as just like one single ray of light. So a little bit of light comes in. Now let's say that that small amount of light produces 200 microamps of gate current. Well, what's gonna happen is, bang, this is gonna fire. All of a sudden, we'll conduct through here, it will energize the relay, and it'll shut the lights off. You go, whoa, it's still almost black. Like it's just a little tiny bit of light on the horizon. I don't want the lights to go off yet. So here's what they do. They say, okay, what we'll do is we're gonna set this resistance to a very low level. And now what will happen is when the first light appears here, let's say that it makes 200 microamps. Well, almost all of it drains off through this resistor to ground. And let's say that the net amount that's actually available here against, in terms of actual gate current is only about 50 microamps. Well, that's not enough, right? So let's say let's say you produce 200 and 150 of it goes this way. Okay. Well, then you only have 50 left here. Okay, so let's say that you have 200 microamps from this amount of light, 150 of it you drain, and so you only have 50, and so you have still not fired yet. So this goes up. All of a sudden, we're going to add some more light. Okay, and this is going to go up to I'm going to say 275 microamps worth of light. Now, okay, so this has gone up. Now we're getting 275. Well, if this is set to drain off 150, how much is left? So you go 150 to 275 is 125. So now we would actually have, instead of 50 here, we would have 125 would be the difference. We're draining 150, we have 125 in the junction. Not enough to fire it. Needs 150. This is IGT. Okay, this is what you need to fire. So you go, oh, okay. So we need a little more light. And sure enough, that takes us over. Let's say this goes up to 325. We're still draining off 150, but it means we have now 175. So we have now enough, and this fires and the SCR starts to conduct. So what did we do with this dial? Well, this is just a sensitivity dial, and you'll see this normally on a photo eye, sensitivity. Normally, you'll see, when you take a photo cell, there'll be a little dial somewhere. You got to dial that thing, and that will adjust your sensitivity to be more sensitive or less sensitive. And what you're literally doing when you do that is you're draining off the current that is produced by the light making that voltage, and you're getting rid of it. And if you actually change this value to a higher value of resistance, then we'll get the gate current we need with less light. Okay, so this is how the sensitivity dial on a photocell actually works. So quite an interesting device. Like I said, normally quite low currents. If you need it to operate much higher values of current, then you'll kind of cascade, we always say cascade them. You'll take a very, very small SCR, maybe operate a larger SCR, and then a relay. So there's many ways of doing whatever you need to do to get the current capability that you need. But in terms of the actual component and how it works, this is really neat. And that's the active component in photocells. So we're getting close, right? These are the thyristors we've talked about. We've talked about the SCR. We've talked about the triac. We've talked about the diac, the UJT, and now the LASCR. And so what that means is that we're not done, but we're getting close to being done with the components. And the only one left that I'm going to talk about in a future segment is we need to take a look at the IGBT, okay, and then that'll be the final component. So that component, the IGBT, is going to be used widely for essentially inverting or creating the voltage output from a VFD. So a very important component, widely used, something that we should know something about. So that's where we'll be moving to next.